we use plastics in almost every aspect of our lives. These materials are cheap to make and incredibly stable. The problem comes when we are done using something plastic. It can persist in the environment for years. Over time, plastic will break down into smaller fragments called microplastics that can pose significant environmental and health concerns. The best case solution would be to use bio-based plastics that biodegrade instead. But many of those bioplastics are not designed to degrade in backyard composting conditions. They must be processed in commercial composting facilities, which are not accessible in all regions of the country. A team led by researchers at the University of Washington has developed new bioplastics that degrade on the same timescale as a banana peel in a backyard compost bin. These bioplastics are made entirely from powdered blue-green cyanobacteria cells, otherwise known as spirulina. The team used heat and pressure to form the spirulina powder into various shapes, the same processing technique used to create conventional plastics. The UW team's bioplastics have mechanical properties that are comparable to single-use petroleum-derived plastics. The team published these findings in the journal Advanced Functional Materials. The researchers says that the bioplastics they have developed using only spirulina not only have a degradation profile similar to organic waste, but also are on average 10 times stronger and stiffer than previously reported spirulina bioplastics. These properties open up new possibilities for the practical application of spirulina-based plastics in various industries, including disposable food packaging or household plastics such as bottles or trays. The researchers opted to use spirulina to make their bioplastics for a few reasons. First of all, it can be cultivated on large scales because people already use it for various foods and cosmetics. Also, spirulina cells sequester carbon dioxide as they grow, making this biomass a carbon neutral or potentially carbon negative feedstock for plastics. Spirulina also has unique fire resistant properties. When exposed to fire, it instantly self-extinguishes, unlike many traditional plastics that either combust or melt. This fire-resistant characteristic makes spirulina-based plastics advantageous for applications where traditional plastics may not be suitable due to their flammability. One example could be plastic racks in data centers because the systems that are used to keep the servers cool can get very hot. Creating plastic products often involves a process that uses heat and pressure to shape the plastic into a desired shape. The UW team took a similar approach with their bioplastics. Other researchers have used spirulina to create bioplastics, but the UW researchers' bioplastics are much stronger and stiffer than previous attempts. The UW team optimized microstructure and bonding within these bioplastics by altering their processing conditions such as temperature, pressure, and time in the extruder or hot press, and studying the resulting materials' structural properties including their strength, stiffness, and toughness. These bioplastics are not quite ready to be scaled up for industrial usage. For example, while these materials are strong, they are still fairly brittle. Another challenge is that they are sensitive to water. The team is addressing these issues and continuing to study the fundamental principles that dictate how these materials behave. The researchers hope to design for different situations by creating an assortment of bioplastics. This would be similar to the variety of existing petroleum-based plastics. The newly developed materials are also recyclable.